All right, let's talk about taking your machine learning models to the next level. We're not just talking about getting a model that works, we're talking about making it truly production ready. We're going from good to great.
Okay, here's our game plan. We're going to start by unpacking a really fundamental problem in machine learning. Then, we'll build up our toolkit, covering how to properly validate your model, tune it for the best possible performance, and tackle some of those tricky real-world data problems you're bound to run into.
So right off the bat, we've got to talk about the single most important challenge, making sure that a model that looks amazing on your training data actually performs just as well when it sees new data out in the wild. That, in a nutshell, is the generalization problem.
This is the question, right? A model's real worth isn't how it does in the lab. It's how it holds up in a live production environment. The gap between those two scenarios is exactly what we're here to figure out how to close.
You've basically got two main troublemakers. On one hand, you have overfitting. This is where your model gets too complex and essentially memorizes your training data, including all the random noise. On the other hand, you've got underfitting, where the model is just way too simple to pick up on the important patterns. Our job is to find that perfect sweet spot right in the middle.
So, how can we get a trustworthy read on a model's performance to avoid those traps? A simple train-test split is okay, but you could get lucky with an easy test set, or you could get really unlucky. To get a measurement we can actually rely on, we need a much more robust technique.
And this is where k-fold cross-validation becomes our best friend. Instead of just one split, we chop our data into, say, 5 or 10 folds. We then train and test the model multiple times, giving us a much more stable and accurate picture of how it will actually perform on data it's never seen before. It really helps smooth out the randomness of a single test.
This visual lays it out perfectly. You see how we're systematically rotating which folds gets to be the test set? This process ensures that every single data point gets its turn to be in the test set exactly once. It's a super comprehensive way to evaluate the model's true skill.
Now here's where it gets really powerful. We're not just getting a single number. Because we have scores from all k-folds, we can calculate an average and a standard deviation. This lets us build a 95% confidence interval, which gives us a realistic range where we can expect the model's performance to land on future data. It's so much more informative.
Okay, so we've got a solid way to measure performance. What's the next logical step? Well, now we try to make it better. This is where we get into the real craft of model tuning.
Now, it's absolutely crucial to understand the difference between parameters and hyperparameters. Parameters are the things the model learns on its own from the data. We don't touch those. But hyperparameters, those are the external control knobs that we, the data scientists, get to set. Things like the depth of a decision tree or the learning rate. Getting these knobs dialed in just right is the secret to unlocking a model's best performance.
So how do you find that magic combination of settings? You don't just guess. It takes a systematic approach, searching through this huge space of all possible combinations to find the ones that really make your model sing.
The two main ways we do this are grid search and random search. On the left, grid search is the meticulous planner. It checks every single combination in a grid you define. It's thorough, for sure, but man, can it be slow. Now look at the right. Random search is a bit more clever. It just samples a set number of random combinations. And it turns out this is often way more efficient.
And here's the brilliant reason why. This landmark paper from 2012 pointed out that usually only a handful of hyperparameters actually have a big impact. A random search is much more likely to stumble upon good settings for those few important knobs instead of wasting tons of time meticulously testing combinations of knobs that don't really do anything.
But here's the thing. You can have the most perfectly tuned model in the world, and it can still fail hard if your data itself is lopsided. This is a massive issue you'll hit the second you leave clean academic data sets behind.
This happens all the time. Think about detecting credit card fraud. Maybe only 1% of transactions are fraudulent. A lazy model could just predict not fraud every single time and get 99% accuracy. But it would be totally useless because it would never catch the one thing we actually care about.
The simple fixes are undersampling, where you just throw away data from the majority class, or oversampling, where you just make a bunch of copies of the minority class. But both have major downsides. With undersampling, you might lose valuable info, and with oversampling, you're just teaching your model to get really good at recognizing the few examples it's seen over and over.
This brings us to a much smarter approach, SMOTE. That stands for Synthetic Minority Oversampling Technique. Instead of just copying data, SMOTE intelligently creates brand new, synthetic data points. It looks at a minority sample, finds its neighbors, and then creates a new point somewhere on the line between them. It's a brilliant way to add more diversity to the minority class.
And here's another cool technique that works from the opposite angle: atomic links. Atomic link is basically a pair of data points from different classes that are super close to each other, creating a confusing, messy border. This method cleans things up by finding these pairs and removing the sample from the majority class, which helps to create a much clearer separation for the model to learn from.
All right, let's pull all of this together. We've gone on quite a journey, from a basic, fragile model to something that's robust, tuned, and truly ready for the real world. So here's the playbook. First, always focus on generalization. Validate your model's performance rigorously with k-fold cross-validation. Next, tune your model's hyperparameters, those control knobs, using an efficient method like random search. And finally, always check for class imbalance and use smart techniques like smoke to fix it.
If you follow these steps, your models are going to be dramatically better and more reliable. But, as soon as you master one set of skills, it opens up the door to the next big question. With all these amazing algorithms out there, how do you even know which one you should have picked in the first place?